Okay, so today I want to continue to talk about the S-ARIMA model. Okay, so seasonal ARIMA model. So just recall like the pure S-ARIMA model that we discussed last class. Okay. ARMA PQS. Okay. P is the order of the AR part, Q is the order of the MA part, and S is the seasonality. Okay, so for this model, we write it as this: VP VS XT equal to Q BS WT. Okay, so this is our model. And the VP is a sequence of like the back shifters. To S VP BS. And theta Q BS is equal to 1 plus theta 1 BS plus theta 2 B2S plus theta Q BQS. Okay. So the difference here is like this seasonal model and the non-seasonal model is that we have this S here. And this S appears in the back shifters in both the AR part and the MA part. Okay. So for example, if say like S equal to 12, which is usually what we will use for the monthly data. Okay, then this phi PBS XT is equal to 1 minus phi1. The first is XT minus 12 minus phi2 XT minus 24. Okay, minus all the way to phi PXT minus PS. Okay. So usually like in the ARMA model, what we put here is X minus 1, X minus 2, all the way to X minus P. But here what we put here is X S times 1, I mean 1 times 12, and this is like 2 times 12, and this is like P times 12. This is 12, sorry. Okay, so that's the key difference. And very important difference. And the reason that we want to do this is because our model has a seasonality pattern. So in order to capture this seasonality pattern, we will use like, say like for in this example, like we will use like 12 months ahead data to predict the current period data. And the reason, as I said, is because of the seasonality pattern. Okay. Okay, so now we have set up this S-ARIMA model. Then the next question is, how can we identify this model from our, I don't know, from our ACF and the PACF plot? Does this, do the ACF and the PACF plot of the S-ARIMA model also have like that tails off and cutoff properties? Okay, so that's our next question, and it is the thing that we want to see next. Okay, so let me switch to the R and fit some model, and let's see if this S-ARIMA model has this ACF and PACF properties. Okay. Oops. Okay, so this is R. So ignore like what I already have here. Okay, so let's do this first example. Okay, so put it down here. Okay, let's do this example. So this example is a AR112 model. Okay. Yeah, so how to generate this model? So this AR112 model basically is that the coefficient of xt minus 1 is 0, the coefficient of xt minus 2 is 0, and the coefficient all the way to xt minus 11 is 0, right? And the coefficient of xt minus 12 is not equal to 0, right? So that's a AR1 12 model. This is also equal to a AR12 model. Okay. Okay, so then on this is our phi. So you can see that the phi that we generate is a sequence. Let me put it open for you. Okay. So you can see that the first 11 coefficients that we have is 0. Okay. And coefficient number 12 is 0.9. Okay. Again, this is very different from the standard or the pure ARMA model. In the pure ARMA model, if it is like an AR1 model, like the coefficient we have is like the first leg has a coefficient, okay, and the rest leg does not have coefficient. But here, what we do is like the first 11 coefficient has 0, and coefficient number 12 is not equal to 0. Okay, and based on this, let's generate this AR112 model. This is a seasonality model. Okay, so you can see what I put here. Okay, so this is like the ARIMA simulation. And we say that we want to do a AR12 model. So the order we put here is 12, 0, 0. Okay. And because we are doing a AR12 model, the AR coefficient we use is this phi. The first 11 coefficients are equal to 0, and the coefficient number 12 is equal to 0.9. Okay. And we generate this sequence 37 times. So why it is 37 times? Because we start with like like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 observations, then another 12 observations. So the total is 24, then another 12 observations. So total gonna be 36, right? And we add one more. So that's why we want to do 37 observations, okay? And the frequency, this is important. The frequency we specify it is equal to 12. Okay, so we want it to like rotate like every 12 times. Okay, and this plus 50 is nothing important. It's just like give a different mean of like this as a Riemann model. So just add 50 to this as a Riemann model. Okay. All right. So I think I run this and let's plot it. Okay, so this is a plot what we have. So this is a seasonal AR1 model. Okay, and the seasonality here is 12. Okay, and you can see this is our time. We from like 1, 2, 3, and 4. Okay, we have 37 observations, and from 1 to 2, we have like 12 observations. So basically like January, February, March, April, May, June, July, August, September, October, November, and December, right? And again, we're back to January all the way to December. And again, January, December, January. And you can clearly see this seasonality pattern here, right? So for example, like the January, the observation of the January is really low, right? While the observation of the June and the July in each year is like at the peak, it's the largest among all the observations in each year. And this is true in every year. So you can very easily see this. Okay, so we successfully like plot, or generate this seasonality pattern by using this AR112 model. Okay. All right. So with this model, then let's see what is its ACF and the PACF plot. Okay. All right, so here is the ACF and the PACF plot, or this is the standard, or the, yeah, I'm sorry. This is, the theoretical ACF and the PACF plot of AR112 model, because it is the ACF and the PACF plot we generate from a true AR112 model. It's like the simulation data. Okay, so now let's see what is the ACF and what is the PACF plot. Okay, so you can see the ACF plot. So the ACF plot, you can see that it tails off at lag number 1, so which is 12, right? Because we do it like our frequency is 12. So it tails off at lag number 12, lag number 24, lag number 36. Yeah, and if you increase the lag of your ACF, you will see that it also tails off at lag 48. Okay, so that means the ACF plot of this seasonal AR1 model tails off at lags Ks. Okay, and K is the integers 1, 2, 3, 4, 5, and S is the seasonality, which here is 12. Okay, and just record the ACF plot of a pure AR1 model. If it is a pure AR1 model, then the ACF plot tails off. But here it is different. It tails off at every 12 period, right? It tails off at 12, at 24, at 36, at 48. Okay. All right, and now let's see what is the PACF plot. So you can very clearly see that this PACF plot cut off at lag 12. Okay, so after lag 12, all these lags are within this confidence interval. Okay, and recall like our pure AR1 model. What's the PACF of that pure AR1 model? The PACF of the pure AR1 model is that it cuts off at lag number 1. Okay, but here it is different. It cuts off at lag 12, which can be also think as 1 times 12. Okay, so lag 1 times seasonality 12. So it cuts off at 12. Okay, so from this graph, we can see that the ACF tails off at 12, 24, 36. PACF cuts off at 12. Okay, so that's the AR1 model. Okay. And now let's talk about a MA112 model. Okay. Okay. Let's do a MA112 model. And again, in this MA112 model, the coefficient of the MA part is that the first 11 coefficient is equal to 0. And the coefficient number 12 is not equal to 0. And in this simulation, I set it equal to 0.9. Okay. So we first specify the coefficient of this MA112 model. And then I generate this time series sequence. Okay, so let me go over this ARIMA simulation command again. Okay, so it is as ARIMA simulation. And what we put in here is the order. The order here is 0, 0, 12, right? Because this MA112 model is essentially a MA12 model, but the coefficient of the first 11, the number of the first 11 coefficient is equal to 0. Okay, and the number of the number 12 like coefficient is not equal to 0. Okay, and the coefficient we put is basically what I just said. Okay, and again we generate this time series 37 times, and the frequency we choose is 12. Okay, and this is again usually is a monthly data, and if you do a quarterly data, it is 4. It is usually 4. Okay. So we generate this time series, this MA112 time series, and let's plot it. All right, so this is the seasonal MA1 plot. So you can see here is that it again has like this up and down like patterns. But the things that you can see, it is not, that easy to detect the seasonality. Okay, so recall like in this AR1 model, like this June, this July are the largest in each year. But however, in this MA seasonality model, like this is not always the case. You can see, so for example, you can see, I think this is March. Okay, so the March is here in year number 1. However, the March is right here in year number 2, and the March goes to here in year number 3. Okay, so it is not always at like this bottom. So in year number 1, it is somewhat, it is lower than February, lower than April. However, if you move to year number 2, I think year number 2, this March is actually larger than February and April. Okay, yeah, so the seasonality pattern, if you just look at this raw plot, it's not that easy to detect, even though it actually has a seasonality pattern. Okay, so the best way to detect, say, like whether this plot has a seasonality pattern is that we will look at its ACF and its PACF plot and say that if the ACF and the PACF plots can give us some hint to say that if this time series actually has seasonality pattern here. Okay, so to do that, for the ACF and the PACF of this MA112 model, and this is what we got. Okay. All right, so this is what we got. So you can see that for the ACF plot, it cuts off at leg number 12. Okay, and again, this is different from the pure MA model, pure MA1 model. So in the pure MA1 model, the AF cuts off at leg number 1, but here it cuts off at 1 times 12, at leg number 12. Okay, and for the PACF plot, you can see that it tails off at leg number 12, leg number 24, leg number 36, and also leg number 48. Okay, so it tails off at leg KS, where K is the integer and S is the seasonality. And this is again very different from a pure MA1 model. So in the pure MA1 model, the PACF plot just tails off. Okay, but here it tails off at every like leg K times S. Okay. Sorry, ACF cuts off at 12. Here, PACF. Okay, so what we just do is the ACF and the PACF plot of a AR112 and MA112 model. Is this always true for the other like seasonality model. So for example, can we also find like the same pattern for a AR212 model or a MA212 model? The other is you actually try it yourself. Okay, so I think I will now write down the general results of this pure seasonal model. Okay, so let me switch back. So first of all, the ARPS model, the ACF tails off at lags KS, where K is equal to 1, 2, 3, etc. And the PACF cuts off after lag PS. Okay, so what I just did in R is that we pick P equal to 1 and S equal to 12. Okay, and you can verify what we just did by using this table here. Okay, and for a MAQS model, the ACF cuts off after lag QS. Okay, and in contrast, the PACF tails off at lags KS, where K is equal to 1, 2, 3, etc. Okay. Okay, and for a RMAR PQS, the ACF tails off at lags KS, and similarly, the PACF also tails off at lags KS. Okay, yeah, so if you compare this table with the table of a pure RMAR model, you can see that the main difference is that we have this seasonality here. The seasonality actually makes things much complicated, actually. Okay. Right. So yeah, so but this also gives you some hints. So if you plot a ACF and a PACF of your raw data, or maybe some transformed data, and if you find like some the ACF and the PACF tails off or cuts off at have some like seasonality tails off or cut off patterns, that means your model or your time series has the seasonality in it. And you perhaps want to use a seasonal model to model your time series. Okay. Okay. Yeah, and a little bit of theory about this table. Okay, so why this result? Okay, so why this is a result? Okay, so let's first consider this. What I do is the MA112 model. Okay. So for this MA112 model, which is written as xt equal to wt plus theta wt minus 12. Okay, so we can show the autocovariance, well, the lag is equal to 0 is equal to this, and the autocovariance when the lag is equal to negative or plus 12 is equal to this. Okay, and the autocovariance of all other lags are equal to 0. Okay, so that's why we see that for a MA112 model, the ACF cuts off at lag number 12. Okay. Yeah, basically it's that only this lag has a positive value. All other lags have 0 values. So that's why ACF cuts off at lag 12. And also lag negative 12. Okay, so that's the MA112 model. And similarly for a AR112 model, which is xt equal to phi xt minus 12 plus wt. So this is an AR112 model. We can show the autocovariance of lag 0 is equal to this, and the autocovariance of plus minus 12k is equal to this. Okay, and all other lags has autocovariance equal to 0. Okay, yeah, so that's why you see that for a AR1 model, the ACF plot of it tails off at lags k times s, because only lag k times s has non-zero autocovariance. And for all other lags, it has 0 covariance. So that's why we say this like tails off pattern at every lag k times s. Okay. Thanks. Yeah, and you can try the PACF for AR112 and MA112 models to verify the results. I think it's pretty easy. It's not that easy, but if you understand like the definition of the PACF, it's like just a partial correlation. You can easily see that this result hold. Okay. All right. Okay, any questions here? Okay, now, so we have seen like the setup of the pure seasonal model and how to identify the pure seasonal model by looking at the ACF and the PACF plot. The next question is that, is it possible to combine with the pure ARMA model? Is it possible? The answer is definitely yes. Okay, so we can combine this pure ARMA model with this pure seasonality ARMA model. Okay, And let's give it a name. Let's call it multiplicative seasonal ARMA model, just to differentiate it with other models. Okay, so it's a multiplicative seasonal ARMA model. Okay, and this model can be written by using these backshifters very easily. So we write it in this way. So the ARMA PQ times PQS. Okay. And to write this model, we start with this pure ARMA model. So it's small phi b xt equal to theta b wt. Okay, so that's the pure ARMA model, right? And then we times its seasonality on both sides. This is big theta q s. Okay, so this part is the ARP. This is the ARPS. This part is the MAQS, and this part is the MAQ. So for example, let's do this model, ARMA 01 times 1012. Okay, so what is this model? So this is equal to xt equal to theta w t minus 1. Okay, so this part is the MA1, and this part is the AR112. Okay, so to study this model, we have a couple of things that we want to study for this model. Okay, so first, I mean, not for this specific example, but for a general. For a general multiplicative seasonality model, we have a lot of things that we want to study, and most of them are pretty similar to like the pure model. So we want to study if there's a valid ARMA model. Okay, so we want to test whether it is causal or whether it is invertible. We also want to see if there is parameter redundancy. We also want to check its residual plot. Yeah, and more importantly, or perhaps the most important thing is that we want to check its ACF. We want to check its ACF and its PACF plots. Okay, so we know the ACF and the PACF plot of the pure ARMA model and the pure seasonality model. The question is that whether this multiplicative seasonal ARMA model, the ACF and the PACF plots of this multiplicative seasonal ARMA model also have like this very nice cutoff or tails off patterns. That's the thing we want to know. Okay, so to answer all these questions, I think I will, to use this very simple ARMA 01110 model as an example and go over all this stuff with you. Okay, I think for the first, maybe we do not have time to do the residual plots, but we can do like the causal, the invertibility, the parameter redundancy. Yeah, most of the things are pretty similar to the pure ARMA models. Okay, the difference is this ACF and the PACF plots. Okay, so we will see it. So let me switch to the R to do this for you, to go over this for you. Okay, so I think, let me see the time. Okay, another half hour. I have enough time. Okay, so before we go to this model, I think I want to do a quiz here. I want to do a quiz here of the ARIMA model. Okay. Yeah, before we do this example of this multiplicative seasonal ARIMA model, let's first do a quiz of the ARIMA model. Okay. Okay, have another 1 more minute. Okay, I have all the answers. Okay, so the answer is true. The answer is true. Yeah, so this YT is not stationary. It is not stationary in two ways. The first way is that it has a t. The t is a time here. Okay, so that makes it non-stationary. And moreover, this xt is a random walk. And we know that this random walk is also not a stationary process. Okay, so this YT is definitely not stationary. And how about the difference of YT and YT minus 1? Okay, how about its first difference? The first difference turns out to be stationary. The reason is that if you take the first difference, then this like this time component would go away, right? Because it's just b times t. So this time component would go away. When you take the first difference, it's just like reduces to bt minus bt minus 1. So it's just b, so which is a constant, which is stationary. And this random work, if you remember, is like just xt equal to xt minus 1 et. Okay, so if you do the first difference on that, what you left is et, which is also which is just a white noise, so which is stationary. Okay, so if you take the difference of the YT and YT minus 1, it would take care of the non-stationary part of YT, like this both parts would be taken care of. Okay, so that says the YT and YT minus 1 is stationary. Okay, okay, that's question number 1. Let's do question number 2. Okay, so yeah, so let me say that, so I asked you like, what is the correct order of this model? The correct order of this model is that we want this model to be a valid ARIMA model. Okay, so in other words, it's going to be causal and invertible. Let's have another minute. Okay, so I think I have everyone's answer. Okay, close this, and the poll. Share the results. Yeah, so the answer going to be A. So the ARIMA 011. Okay, so ARIMA 011. So this is a tricky question. Yeah, so there are two ways to interpret this model. One way is to read it as like ARIMA 011. So if you like put this YT minus 1 to the left-hand side, so it's like YT minus 1 equal to like ET and minus 0.5 ET minus 1. Right, so that's A. And you can also read it as ARIMA 101. So it's this is order AR1 and this is MA1. So not take the difference, just treat it as like the ARIMA 101. Or you can think of it as ARIMA 011. However, in order to make this model a valid ARMA model, only A is correct. Right, because you can see this is like YT minus 1. An easy way to think about it is like the coefficient of this is 1, which is not less than 1. So in order to have like this AR part to be stationary, just recall that we need like the coefficient to be less than 1. Okay, but here it is 1. But if you take the first order difference, like do like this integrated operation, then you will see like this YT minus 1 is equal to ET minus 0.5 ET minus 1. And since this 0.5 or negative 0.5, the absolute value of it is less than 1. So that means it is a stationary process. Okay, so that means YT minus 1 is a stationary process. However, if you just treat it as like YT equals like all this stuff, it's not a stationary process. It's not a ARIMA. It's not a valid ARIMA model. Yeah, you can check it by like typing this coefficients into R and ask R to like find the to do this check for you, and you can see only like part A is correct. I mean, choice A is correct. Okay. Okay. So that's the quiz. Now let me go back to the model. Go back to the multiplicative seasonality model. Okay. So that's the multiplicative seasonality model that I want. So this is ARMA 0, 1 times 1, 0, 12 model. Okay. And for this model, I generate like this AR part. The first 11 coefficient of this seasonality AR part is equal to 0. And the coefficient number 12 is equal to 0.8. And for the pure MA part, I just set the coefficient of this pure MA part equal to negative 0.5. Okay. Right, so I think I will write it down here. So this is the model I generate is a XT equal to gonna be 0.8 x t minus 12. Sorry, t minus 12 plus ET minus 0.5 ET minus 1. Okay, so that's a model I generate. The first thing that I want to check is that if this model is a valid ARIMA model. Okay, so to do this, we just ask the R to find the coefficients of a AR infinity and the MA infinity of this ARMA model. Okay. All right, so this is the AR infinity representation of this ARMA model. And you can see that after, I think, the 16, 17, 18, 19, yeah. So starting from coefficient 20, everything is 0. So that means it can be written as a AR infinity model, and the coefficient of all this AR infinity representation would converge. It's not converge, would be less than infinity, okay? And now let's write it to a ARMA to MA model. Okay, so let me put this result a little bit large. Okay, so this is the ARMA to MA coefficients. Okay, so you can see here, actually this coefficient also has a seasonality pattern. Okay, so let me show you here. Okay, so here you can see, I mean, maybe in leg 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so from leg 12, 13, it's 0.8, negative 0.4. And then everything drops to 0. Okay. And I think it's going to be like 12, 24. So in leg 24 and 25, it becomes 0.46, negative 0.32. Okay. And it becomes 0 again. Okay, and then it becomes 0.51, negative 0.26. Okay, and becomes 0 again, and 0.41, negative 0.2. Okay, and the thing that you can notice here is that the first leg number 12, the coefficient is 0.8. But for leg 24, the coefficient is 0.64. And then 0.51, 0.41, 0.33, 0.26. So you can see a decreasing pattern of the leg 12 coefficient. And similarly, you can see like a converging pattern of the leg 13 coefficient. So negative 0.4, negative 0.32, negative 0.26, negative 0.2. Okay, so it has a increasing pattern, but it will converge to 0. Okay, and here I intentionally ask the code to give us 200 coefficients. And you can see like maybe in coefficient, I think this is maybe 190 something, the coefficient becomes 0.03 and negative 0.01. Okay, so you can imagine that if you increase the order of the coefficients, everything would be 0. So that means the summation of all these coefficients would be finite. And that means we can write it as a valid, we can write it as a MA infinity process. And this is a valid ARMA model. Okay. So everyone good with this? Okay. And since this model we do is a ARMA011012 model, so there's basically like no parameter redundancy problem here. Because like in the pure ARMA part, it's just a MA1 model, and in the seasonality part, it is just a AR model. So there's no parameter redundancy problem in this model. Okay, no parameter redundancy in this model because it is this is MA1 and AR112 models because it is a combination. Okay. Okay, so that's the check of whether it is a valid ARIMA model and a check of the parameter redundancy. Okay. All right, so the next question that we want to do is, or we want to ask is, how about the ACF and the PACF plot of this multiplicative seasonality model? Okay, does the ACF and the PACF plot also have this tails off and cuts off properties? Okay, that's the questions we want to ask. So let's plot the ACF and the PACF. Okay, so let me plot it and give you some comments. All right, so the left picture or the left figure is the ACF and the right picture is the PACF. Okay, so what can you see from this ACF and PACF plots? Okay, so I will write it down here. So for the ACF, what we see, okay, so we see it's cuts off at lags 1, right? It cuts off at lags 1. And it also cuts off at lags 12, 24, 36, etc. Right, because you can see it cuts off like 1, 2, 3, 4. Okay. And moreover, it cuts off at lags 11, 23, it's going to be 35. Right, basically this lags 11, 23, 35, and it's going to be 47. Okay, and moreover, it also cuts off at lags 13, 25, 37. Okay, that's the ACF plot. And how about the PACF plot? Okay, so the PACF plot has a large lag. So let's see, it's cuts off at lag 11, so which is this bar here. So this bar definitely is outside of the confidence interval, very, very large. Okay, and it tails off at lags 1 and 12. Only cuts off, only tails off at these two lags. So it tails off at 1, it tails off at 12. Okay, yeah, so you can, just by looking at these two figures, you can see these are actually much more complicated than the pure ARIMA model and the pure seasonal ARIMA model. The combination of them is actually very complicated. And actually there's no common rule for deciding this. Okay? Yeah. But what I think, like from my understanding, okay, so let me first write down. There is no general rule for deciding ARMA PQ times PQS by looking at the ACF and PACF plots. Yeah. But from my personal understanding, we can sort of like combine the ACF and the PACF rules of the pure ARIMA model and the seasonality ARIMA model to decide which model we want to start with, okay? We can use the rule of ARMA PQ and ARMA PQS to decide to find a starting point. Okay. And then you will okay. And then after you have a starting point, then you will fit a lot of models. And for those models, you will check its coefficient of significance, to check the parameter redundancy, and to check this, whether it is a causal and invertible model, and to check the residual plots to find the best model. Okay, so this step is the same. But I mean, to find a good starting point might be a little bit complicated if we want to fit a seasonal ARIMA model. I mean, a multiplicative seasonal ARIMA model. It's much more complicated. I mean, the starting point is much more complicated than the pure ARIMA model and the pure seasonal ARIMA model. Okay, but we can still use like the rules of the pure model as our starting point. Okay, so which is the thing that I want to explain next. Okay, so for the pure, okay, so our model is this, right? It's ARIMA 011012 model. Okay, so for the MA01 part, okay, so which is for the pure ARIMA part, the ACF should cut off at lag 1, right? And the PACF tails off. Okay, so that's the pure MA1 model. That's the pure MA. Let me write this. Okay. And for the pure ARMA 1012 model, the ACF tails off at 12, 24, etc. And the PACF cuts off at 12, right? So that's what we should expect if we just have a pure ARIMA 1012 model. So a pure seasonality ARMA model, okay? And now let's combine what we expect with what we actually saw here, okay? So let me write it down here. So for our model, we find this. So we find that our ACF cuts off at 1, okay? So this is the same as the MA1 model. For the MA1 model, ACF cuts off also at 1. And we also find our model cuts off at 12, 24, 36. This again is consistent with the ARMA 1012 model. So the ACF plot of the pure seasonal model, right? However, our ARMA 01 and ARMA 1012 model does not capture the cutoff at lags 11, 23, 35, and the cutoff at lags 13, 25, 37. Okay, so Oops. Yeah, basically, it cannot cover like this bars. These bars are a little bit like weird, but if you like solve the autocorrelation function, you can show that these bars actually exist. Okay, but it just cannot be covered by looking by using the rule of the pure ARMA and the pure seasonal ARMA model. Okay, so that's the ACF plot. We can see that our pure rule covers some of the bars here, some of like the ACF patterns here, but it does not cover all of it. Okay, and this is exactly true for the PACF plot. Okay, so for the PACF plot, so our model, as I said, it cuts off at lag 11 and tails off at lag 1 and 12. Okay. And for the PACF plot of the ARMA 01 and ARMA 1012, the PACF plot covers what? The PACF plot cuts off at 12 and tails off. Okay, but it does not cover cuts off at lag 11. Okay, so it covers some tails off at lag 1 and lag 12, but it does not cut off, but it does not capture this lag here, lag 11 here. Okay. So again, the general result is that you will use the rule of the pure ARMA and the pure seasonal ARMA model, the rule of the ACF and the PACF of the pure ARMA and the pure seasonality ARMA model to find a starting point of your model. Okay, but that's not very reliable. So that means you need to fit a bunch of models and use all this stuff, like the coefficient of significance, parameter redundancy, causal invertible residual plots to decide which is the best model. Okay, yeah. So any questions here? So you can see that to fit a multiplicative seasonality model, seasonality ARIMA model is actually much, much more complicated than fit a pure ARIMA model or a pure seasonal ARIMA model. Okay, any questions here? Okay. Okay, so if there's no question, I think that's it for today's class. And next class, we will introduce the integrated model into this multiplicative seasonality ARMA model. Okay, so we'll include like the final part, this D part into this model, and we will do some examples to illustrate that. Okay, so I will post this today's R Moodle, and if you have questions about like this last example, please let me know. I think that's not very easy to see by just looking at the ACF and the PACF plot. Okay, so that's it. Okay, thank you.